In the last video, we looked at the following example, right? We looked at the idea of taking a half plus a quarter plus an eighth plus a 16th plus a 32nd, and so on, where we're doubling the denominator each time, or maybe you can think of it as multiplying the whole thing by a half each time, right? Those are supposed to be twos. Okay, so we're multiplying by a half over and over again. This type of series has a special name. It's called a geometric series. So a series where you multiply by the same common factor, over and over again to get from one term to the next. Is called a geometric series. Just write that out. Okay. So this is a geometric series, and it turns out that these are series that we can sum nicely. In fact, that's the example we did in the last video. So we looked at the partial sums, right? Oh, by the way, I can write this as, it's worth mentioning that I could write this in summation notation as something like 1/2 to the nth power, starting at n equals 1, right? Because that's the nth power sort of shows you that you're multiplying by 1/2 to get from one term to the next. Right, that's what I'm talking about right here. So when we summed this, we looked at the partial sums. If you want to actually find the value of an infinite series, the sum of an infinite series, this is one of the most important techniques, is to look at the partial sums. So actually, now I got to change the index. 1/2 to the I. And so that was a half plus a quarter plus an eighth up to plus 1/2 to the n. And we noticed a pattern, right? We said that this looks like it's 1 minus 1/2 to the n. And I want to call that into question a little bit because we didn't prove it in any sense of the word. We just sort of noticed the pattern and we assumed it continued. Yeah, we just noticed not proved. And so, we did something a little bit that, in real math would be considered, in like higher math would be considered not kosher, of sort of just not justifying that the pattern actually works all the time. Because then we took the limit of that expression as n goes to infinity to see that to claim that the series sums up to 1. So I want to see if there's a way, can we justify this without sort of, I mean, there's different ways to do this, but can we justify, like seriously justify that Sn equals 1 minus 1/2 to the n, always, meaning for all n. And it turns out there's a nice way to do this. So let's just think about an example, like what if I just think about S sub 10? Actually, that's too many terms, probably. Let's do S sub 6. A half plus a quarter plus an eighth plus a 16th plus 32nd plus a 64th. Okay. The claim is that equals 63/64. But I want to show this without actually adding, and this is what's like the really cool sort of like idea. And it's kind of the natural, well, you will see why it's a natural idea, because it's we're going to exploit the fact that you're multiplying by a half to get from one term to the next each time. So like, so here's the idea. Here's the sort of like idea. Multiply S6 by a half. So I'm not actually summing. I'm just gonna, I don't want to actually sum these terms, but I want to multiply by a half. So that's a half times a half plus a quarter plus an eighth plus a 16th. See why I didn't want to go up to 2 to the 10th. But then here's what you want to do. Like you want to actually multiply through, right? You want to distribute. So a half times a half plus a half times a quarter plus a half times an eighth plus a half times a 16th. And if we do that, we get, so 1/2 S sub 6 equals a quarter plus an eighth plus a 16th plus a 32nd plus a 64th plus 1. If you double 64, you get 128. So we got that. And you might think, wonderful, good job. But what does that actually accomplish for us? Well, let's put these two next to each other, because you can tell that they share a lot in common, right? Like this part, all of that is in S6, and it's also in half X S6. And so the sort of nice way to write this, the sort of like way that makes it all really compelling is, let me write S6 again. Oh my God, why did that happen? It's frustrating. Okay. Happened before. So let me write S6 again. S6. Okay, I know I'm writing the same thing over and over again, but we just got to do it. All right, and then a half S6. Let me copy a half S6 underneath it. 1/4 plus an eighth plus a 16th plus a 32nd. Yep. Plus a 64th plus 1/128. Okay. Now here is my big move. I'm going to take the whole right-hand side of this and push it over to there. So I moved it over. Okay, because now the slick thing you can do is you can subtract these equations from each other. Let me go ahead and do that, like minus. I'm going to subtract. And notice what happens when you subtract. All of these cancel. And you get S6 minus a half X. S6 is just 1/2 of S6, right? And we're left with a half here, and then we all end up all the way down here with a minus 1/128 because we actually, everything else canceled and we subtracted, so that's a minus sign. Okay, so, and again, I'm not going to actually work this out. What I'm going to do is I'm going to multiply through by 2 on both sides. So we have 1/2 S6 is a half minus 1/128. And if we double everything, we get S6 is, well, we get 2 times a half minus 2 times 1/128. I know I'm belaboring things here, but that equals 1 minus 1/64, which is exactly what the equation says it should be. And that to me is kind of amazing. It's like somehow we were able to add this without having to add anything. In fact, what we really did is we subtracted, I guess, and got a bunch of stuff to cancel. But that agrees with the formula up here, right? And so that's called a finite geometric series, this sort of thing where we actually stop. And this kind of technique actually always works, which is kind of nice. So let's do another example. another example of a finite geometric series. Let's start with the number 5. And let's just multiply by 2/3. So I get 10/3. If I multiply the top by 2 at the bottom by 3, 29ths, 40 over 27, 80 over 81. Oh, is it worth doing one more? No, let's not do it. I guess it'd be 160 over 243, but I don't really care. And oops, I forgot to put my sum. Let's just call this S. But let's see again if we can add this without adding it. So this is times 2/3 times 2/3. Each of these I'm multiplying by 2/3, right? Okay, so if I write S and then underneath it I write 2/3 S, because think about what 2/3 S is going to be, right? So 2/3 S will be 2/3 of this sum. Like we're going to end up with the 160 over 243. So I'm glad I stopped where I stopped. And, you know, again, we're going to distribute. And so we get 10/3 plus 20 over 9, right? From the first, like when I'm the first time I get 10/3, the next time I get 20 over 9, and so on. So I multiply 29ths by 2/3, I get 40 over 27, 80 over 81. And now I get 160 over 243. At some point, you could just start writing 3 to the 5th, you know, instead of 243. But again, we have that thing where we have a lot of overlap. So S contains these 4 terms, and 2/3 S contains the same 4 terms. It's just one term off. So when we subtract, okay, I won't actually copy it this time. I'm just going to say, like, you can sort of see what happens when we do S minus 2/3 S. We get 5 plus all this stuff minus all this stuff minus 160 over 243. Right, so everything in here cancels. This is the stuff that I put a red bubble around. All that cancels. And so that means when we subtract 2/3 S from S, we're left with 1/3 S. And that's 5 minus 160 over 243. And if we multiply through by 3, we get S is actually 15 minus, multiply by 3, actually cancel one of the 3's in the bottom, so I get 160 over 81. So that's some number. I mean, in fact, this is fine. This is, I don't really care about, I guess I can simplify it if I wanted to, but it's probably 13 plus 2 over 81 or something like that. So it's just a little more than 13. But that's good enough. Again, I added without adding. So that ends up being that sum. And we can do this in general. So there's like, if we wanted to write a general, so there's something called the finite geometric series formula. But again, it's not the thing where I just want you to know the formula. I want you to actually know the derivation where it comes from. So if we generalize, think about what a general finite geometric series looks like. This is the way we tend to write it. Start with some number A, like the 5 in the previous example, and then multiply by R. That's the 2/3 in the previous example, and then keep multiplying by R. And let's just do that until we get up to A R to the N. Okay. So let's call that, oh, I forgot to leave room again for S sub N. So this actually has N plus 1 terms, because you can think of the first term as like A times R to the 0 if you want. but most books tend to use A and R. A is the first term, and R is the multiplying factor. Okay, so, and as this is a finite geometric series. Let's do the same thing. We'll multiply through by R, right? So let me just copy the formula down here. Sn A plus AR plus AR squared plus dot, 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 plus AR to the N. And if we multiply by R, we get AR. So I'm going to go ahead and, well, okay, I'll be fancy. We multiply each term by R, right? AR plus AR squared plus AR cubed plus, well, I have to be a little bit careful here. AR to the N plus 1. To actually spread this out a little bit. Let's spread this here. Let's be generous. And so in fact, if I move this over to here, maybe I have enough room to put in, ooh, I picked up one of my dots, but I have room to put in plus AR to the N as the previous term, right? That's the term that would have been just before that. And then I can take the whole thing and push it over so it all lines up nicely and subtract. And we get, well, let's just deal with this in a second. We get S sub n minus R times S sub n. And then we get A here, everything else cancels. Right, even the A to the n's cancel. And we get minus A R to the n plus 1. And then we can think about how to deal with both sides. We can factor out the S sub n on the left, right? So we could factor out S sub n and be left with 1 minus R. We can factor out the A on the right. And so in fact, we get this formula called the finite geometric series formula, that it's A times 1 minus R to the n plus 1 over 1 minus R. And that's the finite geometric series formula. We could check it against the examples we've done. Not sure if it's going to be super obvious, but the examples, the first example that we had, actually the first term was a half. And R was a half also, if we go, I'm going all the way back to the beginning of this. And we actually, N was 6, right? Yeah, we did S6. So, okay, so N equals 6. And that means S6 is, well, it's a half times 1 minus a half to the 7th over 1 minus a half. I actually get a half on the top and a half on the bottom. 1 minus half is a half. Those cancel. Wait, did I mess up? Oh, actually, it is not 6. This, okay, this is an important point, and I'm sort of glad I messed up. This has n plus 1 terms in the sum. I actually sort of said that I thought of this as AR to the 0, the first term. That's n plus 1 terms in the sum. So S sub n has n plus 1 terms. So I probably shouldn't have even called this S sub 6 before, because this only had 6 terms in it, right? This sum had only 6 terms in it. So it's actually like, it's almost like I should have written a half times 1 plus a half plus a quarter, all the way up to 1 over 32 or something like that, if I want to keep it kind of the same. So, and there's the 2 to the 5th. So that's why it's really like 5 terms. Okay. So you got to count the number. You got to count this kind of correctly, because if you do it this way, this is actually, honestly, this is why I like not plugging into the formula. This is actually a good illustration that you should just do the derivation. Plugging into the formula can mess you up. So in fact, okay, so what do I want to say? This isn't really, this is kind of a 5, n equals 5. Oops. So that's really a 6. Okay. And so 2 to the 6 is 64, which is why I noticed that was going to be wrong. Okay. Again, just use the derivation. So that ends up 5. 1 minus 1 over 2 to the 6th, which is 1 minus 1 over 64, which is what we got. And if we do the second example, I think it'll be more natural because we actually start with a kind of a random number 5, and r is 2/3. And did I use 6 terms again? How many terms did I use? 1, 2, 3, 4, 5 terms. Okay. Although that means n is 4, right? I mean, again, that's why it makes a lot more sense to just derive it and not use the formula, because we go up to 2/3 to the 4th, right? Right, we get 5 plus, let's just call this S. We get 5 plus 5 times 2/3, and the last one is 5 times 2/3 to the 4th. And so the geometric series formula says our first term is 5, 1 minus r 2/3 to the n plus 1, which is 5, the 5th over 1 minus 2/3. This becomes 1/3 on the bottom, divided by 1/3 same as multiplying by 3. So this whole thing is 15 times 1 minus 2/3 to the 5th. Is that what we got there? Wait a Oh my God, I actually screwed it up all the way back here. Oh my God. That's terrible. This is why I shouldn't skip steps. When I multiply the 3, this actually becomes there's a 3 up here. So this is really 480, which is 3 times 160, which is 3 times 5 times 32, actually. So it's 15 times 32. So that's where, so the 15 is going to come in. Okay, so don't mess up basic algebra if you want the right answer. But you know, either way, you have to do things kind of right. So 1 minus 2 to the 5th is 32 over 3 to the 5th, which is 243. So it actually is the same answer as we had before, because I could factor the 15 out. So yeah, this ends up being 15 minus 15 times 32, which I had up there was 480 over 243. I have just completely, oh my God. I'm really screwing everything up. The whole point. Wow, this is a bad video now. Okay, I'm just giving you reasons why not to use the formula. I actually did do this correctly back up here because I multiplied. Oh my God, this is so bad. I multiplied the 3 times this, and I actually canceled with the 243 and had an 81. So in fact, it was good. It was good the first time. Shouldn't have second guessed myself. 15 minus 160 over 81 was correct. And here, yeah, this is 15 minus 40 over 243, but that's, I can factor 3 out of the top and bottom and get 15 minus 160 over 81. Okay, I hope I made the point that you shouldn't use this formula. You should just rederive the You should just go through the argument and multiply through and shift everything over. It's such a nice argument, right? The argument up here, for example, so nice. Multiply through by the 2/3, you shift everything over, shifts all the terms over, and you get this sort of first term minus this last term, and you're done. Okay, so this has been your nightly comedy of errors, but maybe there's a good point to take from it. So enjoy. Okay, bye.